Hello friends, this is Shravan Kumar Manthri. Welcome to our channel CSE GURUS. In our previous video lectures we finished like selection sort, bubble sort, insertion, merge and quick sort. So now we'll see this heap sort. So what is this heap sort? Of course it is related to non-linear data structures, that is trees, especially binary trees which are complete binary trees. Okay, we will see all those things now regarding this heap sort. Yeah, here we can see heap sort. It can be done using complete binary tree. So if you want to know about heap sort, you first have to know what is a complete binary tree. Then after knowing this, what is complete binary tree, after arranging the elements in complete binary tree, you have to create a heap tree. So what is this heap tree? That also you have to know. Then you have to sort the heap tree so that you will get the elements which are given in sorted order. So while constructing heap tree, you can either go for max heap or min heap. So anyone you can go, and we have to know all these things. Like the first thing is what is complete binary tree. I'll discuss this one. Then how to create a heap tree, I'll discuss with the example, of course the procedure. Then I'll show you the program with execution and output. Finally, what is the complexity if you go for this concept of heap sort. So all those things we'll see in this video. So moving on to the first, that is complete binary tree. So we know about trees, like tree has nodes, then of course like this nodes will be there, and nodes are connected with branches. And binary tree, if I say, that means for every node you have at most 2 children, right? So if you take this one, 2 children, and if you take this one, 2 children, if you take this one, 2 children, like this, 2 children at most. And you may have less than 2 also, that is 1 or 0, but not greater than that. You may not have like this, right? You cannot have definitely like this one more node, or somewhere here like this. You can have one node here, right? So for this no children, right? So you can have one node. That is also a binary tree. The condition is you should not have more than 2, right? So this is about binary tree. And now you can insert the elements in a binary tree in general. So how this can be inserted? Let me take some example. Like let us suppose I'll take an element like 5. If I take 5, initially it will be a root node. Then I'll insert it some element like 4, it will come here. Next I want to insert something like 3, it will come here. Next I want to insert something like 8, so it will come here. So I'm just inserting like this. So in a programmatic way, in a technical way, how we can, graphical way we know that okay, these things how you can insert, but in technical way, in programming way, how you need to represent all these things. Let me take the example of arrays in a basic. So let us suppose if I take arrays where the index starts with 0, okay, where the index starts with 0. Let us suppose this is a node 0, this is a 1, this is 2, this is 3, third element, fourth. Let us suppose like this I am inserting everything. Okay, it may go like this every time. So like this the nodes will be there. Let us suppose if I want to create an array of 15 elements here. So like this the elements will be there. I can take this one. Now we have to know, let us suppose this is an array. I'll take, so like this elements will be there, starts with 0, 1, 2, 3. Now I can see what is a parent of 4 means you can say it is 5. What is a parent of 3 means it is, you can say it is 5. Now if I ask you what are the children for 5, you can say 4 and 2. So children for node 0 is 1 and 2. Children for node 1 is 3 and 4, right? So I'll write clearly here. For 0 it is 1 comma 2. For 1 it is 3 comma 4. For 2 it is 5 comma 6. How can you relate them? How can you relate them? Can I say like for a parent I, the nodes, the children which are 2i plus 1 and 2 into I plus 2. Can I say? For 0 you can say 2 into 0 plus 1, 1, 2 into 0 plus 2. For 1 you can say 2 into 1, 2 plus 1, 3 and 2 into. So like this you can get the children, the representation. Whenever you know you are at a node I, if you want to get the children of a binary tree, you can write simply 2i plus 1 is the first one left child, and 2i plus 2 is the right child. So like this you can represent in a binary tree if you take it in an array. And let me take some other examples. Like let us suppose I want to insert like this 5, 4, of course I inserted 3, then 8 I inserted. Okay, yeah, now I want to give a space here, let us suppose. So that means I don't want to represent an element here. This means -1 means here you won't have an element. Here you won't have an element like this. Okay. Or if you want to represent like this 5, 4 and 8, immediately here you will get 8, right? So like this it will come into picture. Okay. Let us suppose after 8. Okay. Let us take here as 3 again. Here I'll take 3. Then after 5, 4, 3, 8, then next element is not there. Let us suppose -1. Here next element is not there, -1. Let us suppose here I want to insert something like 6. So 6 will come here. So like this you can represent the elements in a binary tree in terms of in an array. So this is also important why I am explaining all this, like the representation in an array like this. So where the indexes like this I can write. So now the thing is, what is complete binary tree? Of course I need to compare this one with full binary tree also. What is full binary tree and what is complete binary tree? Okay, so it is, let us suppose if I first go with the full binary tree, it is with respect to the levels. So each level it should complete. That means let us suppose if I take the elements in a binary tree, so if you take a level, the last level must be completed. Anyway, in the middle levels also should be completed. Let us suppose if I have the elements like this, only 3 elements, let us suppose 5, 4, 3 I have. So now I inserted 5, then 4, then 3. So now you can see the level 0 is finished, level 1 is finished, level 2 completely empty, right? It's not half filled. So like this if you find, I can say it is a full binary tree. If I take the next level, all must be filled. Like I need to have something like 8 here, something like 10 here, something like 7. Why might be, and something like 3 here. So now I can say it is a full binary tree. If someone is not filled, so I cannot say it is a full binary tree. Somewhere it is not filled, somewhere it is not filled. Now also I cannot say it's a full binary tree. So it's not. So whenever you take a level, that means at the last level, till that last level it must be finished. So you can have a formula also, like for full binary tree you can see here. So that means a binary tree of height h that contains exactly 2 per h minus 1 elements is called a full binary tree. Here you can see this is a level 1, you can say this is a level 1. If I consider what is 2 power 1 minus 1, 1, and here this level if I say, okay, what is the second level? If I take h is a height, that level height starts from 1. Okay, it is 2 power 2, totally 3 elements you have, right? So 2 power 2, 2 power level height is 1, 2 minus 1, which is like this. And if I take third level, so 2 power 3 minus 1, which is 7. So complete the elements has to be filled, then I can say it is a full binary tree. So it should not be like half filled, somewhere it should not be. Okay, yeah, so this is full binary tree. So what about complete binary tree? Okay, here you can say it's a special case of binary tree in which all the levels except the last level. So all the levels except, what is the last level? Here you can see this is the last level. So this last level is not completely filled, but the remaining all levels are finished. You can see for this 2 children, for this 2 children, for this 2 children, here for this, of course, but the last level is empty. But there is also one more condition. You can see any missing nodes to the right of all the nodes that are present. So if you have any missing nodes in the level, that must be at the right side. That means the last level must be filled from left to right. So let us suppose here I don't have this element, let us suppose, or this element both, and these elements are here 8 and 9. Now you can see 3 levels are filled, but the last level you can see half filled. In this case also I cannot say it is a complete binary tree. Why? Because I told you, like, any missing nodes should be on the right side but not on the left side. You can see these nodes are filled, these nodes are unfilled. So like this, that means every time, let us suppose if I take the node numbers like this, first this node to be filled, next this, next this, next this, next, like this, it has to follow. Then only I can say it is a complete binary tree. If any missing nodes are there, then I cannot say it is a complete binary tree, like this on the left. Okay, even let us suppose if I don't have these elements, okay, then these elements are also not there, then also I can say it is a complete binary tree. And of course it is a full binary tree also if I don't have this one also. So that is what, every time the filling must go from left to right in each level. Okay, and in the middle you should not have any element unfilled, and the right side you have elements with. So that is what the example of complete binary which we are using in the concept of heap now. So here also I am feeling like, let us suppose if I write like this, 5 4 3 8 minus 1 minus 1 6. What is the meaning? 5 4 3 here, 8 here, then here it is minus 1 means no node, here minus 1 no node, here 6. So can I say it is a complete binary? No. Can I say it's a full binary? Of course no. So you can see for complete binary 5 4 3 then 8, then here this must be filled. Okay, let us suppose this field is filled with 7 and here it's not there, then I can say this is complete binary. So it is filling from the left. Now I have, let us suppose some element here as something like 6. Now it is also fine. So right side it is empty and left side it is filling. So now also I can say it is a complete binary. Of course it's not full till now. Now one more element, if I take something like 10, yes, now I can say it is complete as well as full binary. Let us suppose I'll take 15 here. Now it is complete but not full. I'll take here 10, something like 12. It is complete but not full. So when it will become full binary now? So all this must be filled. So let us suppose if I write something like 20 here, now it is not a complete binary, of course not a full binary also. So this, why it's not a complete means these are empty. So like this it should not be, right? So this is what we call it as the concept of complete binary tree. So like this we can represent, and we can see this is we called as complete binary. And now we'll see this complete binary, how this can be useful in the concept of heap. Yeah, first we'll see heap tree, how to construct, and of course I'm going with max heap. Okay, I'll tell you what is this max heap, and afterwards we'll go for min heap. Okay, so the max heap is nothing but whenever you construct a tree, so the node whichever you take, okay, all the subtree, all the nodes of the subtree must be less than your node, your root node, or for any subtree if you take, all the subtree elements must be less than the root node for each subtree. And for min heap it is in reverse. Let us take one example, like if I take something like 70 here, I'll take something like 20 here, something like 50 here. Now I can say it is a max heap, right? The sub nodes. Let us take here 10, here I'll take 5, here I'll take 40, here I'll take 30. Then also I can say it is a heap, max heap, right? For 70 all are less than, for 20 the sub nodes are less than, for 50 sub nodes are less than. Okay, so now can I take like this here? Let us suppose I don't want to take this element, and now I'll take one more element here 2. Can I say it is a max heap? First of all, it is not a complete binary, right? So here this node is missing, so that's why first of all it is not a complete binary. So like this we need to remember. And let us suppose here we have 5. Now here this node is not there. Can I say now it is a complete binary? Yes, it is a complete binary. It is a max heap also. So like this we can have. So this is what about max heap. So what about min heap? Min heap means completely reverse. So the element which you take for each node, the root node, the subtree, all the elements must be greater. So you can take a simple example like 10 will be there, here something like 20, or something like 30. Okay, yeah, here something like I'll take 50, then 60, here something like 80. So this is what, like this if I found, this is we call it as min heap. For every subtree the root node value must be less than all its descendants. So like this you can check it out. This is we call it as max heap, this is we call it as min heap. This is max and this is 10. So this is we call it as min heap. Now we'll construct heap tree. Let us suppose we'll take these elements. So for these elements we'll construct what is the max heap. How to construct the max heap? So first of all, what is the element I have to take? 50, which should be at the root node, you can see. So 50 I have taken, which is anyway here in this example he is starting the node value, that is array, from 1, because of sometimes you may get confusion, but you can take at 0th index also. not at all an issue, you can take. So let us suppose it started with 1. So 50 is a root node, only one node directly has taken, there are no conditions. Now the thing is the next element 25. So anyway, first you have to insert here, right? So this is the 0th index. Okay, next you have to come, this is 0, then this is the first. That means, okay, anyway in this example it started with 1, right? So like that also you can take. Anyway I'm taking with 0, so 1 the next position. Now the next element, anyway one more thing you have to check it out, is that 50 is greater than 25? Yes, true. Why? Because for max heap the property has to be maintained. If not, what you need to do, you have to do the procedure of swapping, right? So let us suppose the new element is 75, you have to insert first, then what you need to do, then swap it to get the, to maintain the heap property, that is a max heap property. So now the next element 30, anyway first I need to insert 30 here, then you have to check it out, the property of max heap, is it following? Yes, it is following. Then I can insert and no need of any further operations. So then it will come like this. So 50, 25, 30. Okay, now the thing you can see 75, next element is 75. Where must be taken first? You have to take here, right, the position, that means 0, 1, 2, then 3, like this. So here 75. Now you check it out, is it a max heap property? No. 75 with parent you need to check it out. 75, 25. So 75 should be top of 25, right? So that's why you have to do swapping. So here 75 will come, here 25. This process has to be done. And now 75 you have to check it out with 50 also. Why? Because here also it is not same. Until you have to go to root node, you have to check it out until this condition is false. So now here 75, here 50, right? So it is not following the max heap, that's why I made swapping operations. So now that resultant tree will become like this. You can see when I get 75 initially inserted here, then 75 with 25 swapping, then 75 with 50 again swapping. Now you can see 75, 50, 30, 25. Now it is following the property of max heap. You can see for 75 all the descendants are less than, and 50 descendant is 25 is less than, right? Yeah. Now the next element 100, where to be inserted? First of all I'll see. For this one 100 to be inserted initially here, right? The next position, position in the level. So now 100 with the parent 50, you have to swap, right? And 100 here it will come 100 with 75, again not following. So 100 again swap. So like this it will come. So 100 initially inserted here, 100 with 50. So 100 50 is less than, that's why swap, and 100 with the parent again 75. So again swap until they're reaching to the root node. So now it will be like this. Now check it out, is it following the heap property max heap? Yes, true. Now the next element 45. So where 45 to be inserted? Here, right? The left of the parent 30, right? So now you can see, is it following the max heap property? No. 45 is greater than 30, so swap it. So 45 will come here. Now 45 with 100, is that 45 is less than 100? Yes, true. So no need to swap here, right? So you can see now 45 came here and 45 100. Yes, max heap property is maintaining. That's why one more swapping is not required. Only one comparison and swapping is required. Now the next one 45 is over. Next 80. So how 80 can be taken? Where it has to be taken? Anyway 80 has to be taken here, right? So first 80 has to be taken here. 80 and 45 not following the property. So this value should be less than this one, right? But not. So that's why swap it. 80 will come here. Here and 80 and 100. Yes, 80 is less than 100. So no need of that. So finally it will be like this, right? So when I go with 80 initially here, then swap it. Then finally for this one, for this array with 7 elements, the max heap will come like this. The elements will be stored like this. Anyway, remember when you go for max heap property, if you store it in an array, in between you won't find any empty cells in between. -1 like this I explained now. So in between, then only it is a complete binary tree. So now we are maintaining like this, and we got heap tree first of all. So we got only heap tree, which is a max heap I maintained, and now there is a task to do for heap sort. Okay, so these are the elements, we got it. Now we have to do, so let us suppose these are the elements I want to sort. So I need to get the output as, what is the output if I get the sorting finally? 25, 30, 45, 50, then 75, then 80, then 100, right? So this has to be maintained. Anyway, for this, let us suppose if I insert one more element, let us suppose something like 32, what happens? 32, or else I'll take 132. Let us suppose 132 will be taken here, right? Left of this one, this is filled right here. So 132 you have to check it out with 75. So it is 132 is greater, that's why swap 132 with 75, again swap 132 with 100, again swap. So like this process has to be continued for all the elements. Now we'll go for heap sort. Okay, forget about this element now. Yeah, now we'll go for the concept of heap sort with the heap tree. So how this can be done, we'll see. So this is a resultant heap tree we got, this is a max heap we got. How you have to do this heap sort, and remember a word like heapify. So this is a very important word, heapify. This has to be done. So how you have to do? Anyway, this is an array. Okay, I'll take this array where index starts from 0. Now how to do this one? So you may think of like, whenever I want to get the sorting, will you start from the last element? So not exactly, not so correct. Okay, always remember the point in heap sort, you have to start with root node. What is the root node? 100, right? Yeah, so you have to start with the root node, and this root node you have to immediately swap with the last element. So what is the last element? 45. So anyway 45 will be stored, right? So this is the index 0. Let us suppose 1 2 3 4 5 6, like this we have elements here, let us suppose. So now you have to swap. So what happens here? Here 45 will come, here 100 will come. So 100 means in A of 6, right? So I'll take 100, the largest element at the last position. So 100 will come here. Anyway, this node will be removed like this. Okay, 100 will come, this node will go, and then here 45. Now what you need to do after making 45, now you have to check it out, is it a max heap? Now definitely here you can see it is not, right? Why? Because you can see 45, all the descendants should be less than, right? You can see it is not following now. So you have to check it out whether this value to be swapping with this one or this one. Might be a confusion for you, right? So check it out. A simple solution, like first find out what is the largest of this one. What is the largest of these two? 80. So swap with that. Whichever is the largest, that you swap. So 80 is the largest, that's why 80 here, 45 here. Okay, so like this. Now you can see what is the result, and you will get, I'm writing here 80 here, 75 here, 45 here, 25 here, so 50 here, and 30 here. Anyway, that 100 I kept at the last, and I'm ignoring that, so which is at the last. Now the thing is, this process has to be continued. So heapify means, so you deleted and you adjusted, right? Adjusting means what happened? That means the element is deleted, element is swapped, then checking with whether it is following the heap property, that is heapify we call it as. Now again do the same process. What is the root node? 80. Okay, you have to swap with the last element 30, which is the index is 5, right? So 30 here, 80 here. So 80 will be at the 5th position. Now 30 here, again check it out. Is it following the heap max heap? No, right? So that's why heapify you have to do. So 75 and 45, which is the largest? 75. So swap with 75. Here it will be 75, here it will be 30. Now the resultant will be like 75, 30, then 45, then 25, then 50. Anyway, the element 80, which is I'm ignoring, which is stored at the last position. Now this process, next one, you can see what is the last element? 50, swapping with 75, 50 here, 75 here. Okay, now you check it out. Is it following the property? Yes, it is following. Why? Because you can see for 50 all the descendants are less than, so directly no need of any swapping here. Anyway, 75 at the last position, like this, right? So now the resultant is, I am writing here 50, 30, 45, then 25. Like this we have to do. And now you can see what is the last element. 25 swap with 50, so 25 here, 50 here, so 50 in this position, A of 3. And now is it following the property of heap, max heap? No. So 25, 30, 45, which is a max? 45. Swap with 45, you have 25. Now you can see that's it over here. So the resultant is 45, 30, then 25, right? So now the next, the root node 45, you have to swap with 25, right? The last element. So now you can see 45, 25, I'll swap 25 here, 45 here, so 45. Now the thing is 25 and 30, is it following the heap property, max heap? No. Why? Because here you have to 30 only, here 25, 25 is great less than 30, so swap here directly 25. Now the resultant is 30, then 25. Anyway, now only two elements. Now you can do 30 and 25 swap with, anyway it's the last element, right? So here 25, here 30, this 30 will go here like this, and finally this also will be deleted. Only one element 25, finally this will be written here. Now you can see your array. Can you see all the elements in sorted order? So this is what it can happen in the concept of heap sort. Like this we have to do every time. And remember the point, always root node you have to take, that can be taken out, of course, by swapping with the, by inserting at the root node, taking that element in the last index of the array, and in the root which value to be taken. It's not like comparing directly, it's first you have to take the last node in the tree, you have to take it, then check for is it following the max heap property. If not, swappings can be made, like in general how you can do heap tree construction. So like this we need to finish it up. So like this we can complete the concept of heap sort. So now we will see the coding part, how to write the program. And most of the time you can use in the concept of queues. If you go for concept of queues, you have to go, you can easily implement with priority queues. So the concept of priority queues, where you can have the priority which has to be taken first. So if you go for priority key, it will be very easy for making this heap sort or constructing this heap trees. So like this. And anyway, I have written the program in C, and we'll see that program and execution. Yeah, now you can see here. So the program anyway I have taken. So initially these are the elements, input elements, n number of elements, and I am taking here. And now heap sort function I have written here. So this goes here, heap sort function. And now you can see this one, for I equals to n minus 1 by 2. What is this n minus 1 by 2? Let us suppose if I have 7 elements, what is 7 by 2? Which is 3, right? So that means you can see here 7 elements, which it needs to start 0, 1, 2, 3, 4, 5, 6, right? So that means 7 by 2 means 3 minus 1, right? So of course 7 minus 1 by 2, which is 6 by 2, right? So 6 by 2, which it has to start, actually. And now you can say n minus 1 by 2 it has to start, means for this one you have to check it out if there are 7 elements here. So that means you have to take whatever the last node is there, what is the parent of that last node, from there you have to first go, and check it out. So anyway here the thing is that n minus 1 by 2 you have to check it out, and see this one heap of I comma n, you have to check it out, and here it will go. So let us suppose if I take this as element, the parent is 2, from that it has to start, right? So from that it will start. Now here if I take these elements, Yeah, here we can observe here heap sort of n minus 1 I am giving the input. If 7 is my n element, 7 minus 1, 6 here, that means high value is 6. Here 6 minus 1, 5. So 5 by 2 which is 4, right? Sorry, 5 by 2 which is 2, right? So for the last node, what is the parent? 2. So that you will get directly. So this is what you have to check it out first. So n minus 1, 7 elements are there. 7 minus 1, 6. So here 6 minus 1, right? High means n value, n equals to I, right? So 6 minus 1, 5 by 2 which is 2. So like this, that means I'm going to the parent of the last node. I'm checking the values. I'm checking the values first. Okay, yeah, first I need to, anyway I have to make rearrangements, right? So initially I have to make rearrangements, then only I can go for heap sort, right? So that is what here happens. You can see, first of all I am going to this node, and here you can see if child is less than or equals to 10, this part you can see, this part is actually a of child is less than a. That means if I take this node 30 and 45, okay, 30 and 45, which is the least value I'll take, okay, which is the least value. That means if a of child 30 is less than 45, right? So child plus plus I am taking 45. So that means whichever is the greater, that I am taking for this nodes. Okay, whichever is the greater I am taking and checking with else part. See, this is completely for heapify to adjust. Actually the whatever I have taken here, this is already adjusted, right? If it is not so, then this process has to be applied. Okay, let us suppose if I take here something like 30, 32, 30, 45, let us suppose. What should happen actually? 45 should go here and 32 should come here, right? Now you can see this part, you will get the answer. Okay, so first checking a of child is less than. Now I am checking these two, which is the largest. I am checking with this. If this is the largest of these two, no need to update anything. If anyone is largest than this, that will goes as a parent, right? So that process will be applied here. You can check it out clearly, line by line, that will happen here. Let us suppose if I have here the value 80, so 80 is greater than both of them, then directly you have to do nothing. You have to do nothing and go up and check it out with this. Okay, sorry, go down and check it out with the next one. Okay, and if this element is less than any one of these, then swapping can be done. Of course this has to be made whenever you make swapping. Like let us suppose first what we have to do, 100 can be taken, right? Okay, so you can see first you have to do heap sort, and anyway it is fine for the first time. Then I equals 10 minus 1, the last element swapping, you can see. So 45 I told you, no, swap with the root element a of 0. So 45, this swapping I am doing now. So 45 will be here, 100 will be here, right? Now you can see this part, then heapify of a of 0 comma I. What is a of 0? 45. Now this has to be done swapping with, this with the remaining elements. So now what should be done here? You can see root and n. Now this process, that means 45 I am checking. 45 I am checking with 75 and 80. This one is that 75 is less than 2 childs, right? 2 children. So 75 is, which is greater, I am taking. Okay, if 75 is less than 80, then I am child plus plus taking this one. Definitely this will be greater. Now here I'll come. That means key means our value. If 80 is greater than 45, that means I am definitely checking among these three which is the greater. Okay, 75 and 80, which is the greater? 80. 80 and 45, which is the greater? 80. That means child is greater. That means swapping will be done here. Okay, now a of child minus 1, this part will be executed. Okay, yeah, else part will be executed if key is not greater, right? So this part will be executed and swapping will be done. Here 80, here 45 will come. Here 45, when it will come, again you can see after this process, while child is less than, this process has to be continued. 45, now you have to check it out with the next one. Okay, this while loop will be completed while child is less than or equals 10. That means n value is now, it has, anyway here you can see child equals child into 2 plus 1. That means here the 6 into 2, 12, right? It is going beyond. That's why it is coming out child minus 1 by 2 equals to key. That means here you will have 45 when it goes out actually. So now you can see for 45 also you can see 45 with here what you have the value, only one value now. You can see after this one is eliminated, you have 30. So 30 is greater than 45. No, stop here. Okay, so like this it has to be done. Next, taking the next root node 80, it will come here. 80 you have to swap with this, right? So when you swap 80 with 30, the last element, 30 will come here, 80 will come here, right? Now 30 with you are checking 75 into 45, which is the largest? 75. This will be done here. Okay, 75 is larger, that's why swap here, 75 here, 30 here. Now here again it's not making, so again this process will continue. You can see, okay, while child is less than or equal to, whenever it is, okay, e of child 25 and 50, which is less than, which is greater? 50 is 30. Okay, 50 is greater, so 50 will come here, 30 will go here. So this process. Next, what is the index? 4 into 2, 8, which is going out of that, so that's why it comes out. This condition will be false. So this process every time will continue. Okay, for this heapify, every time the element will be taken finally, and after heap sort every value will be rearranged, and after that directly. This is all about rearrangement, right? So I am not taking any extra auxiliary array. This is all about rearranging. So like this we have to do for this heap sort. Okay, if you go for a priority queues concept, you can write a better code, but this is a code which is written in C language. Anyway, we will execute this one. This will execute successfully. You can see the output now. I copied everything. You can see two functions, heap sort and heapify. So first taking the elements here, then heap sort, here it is. So here heap sort, in that heapify to adjust that one. So when heapify called, it will go here and heapify will be maintained everything I copied here. We'll see the execution, the output. Yeah, enter the size of an array. So we'll take 8 elements. So something like I'll take 20, something like 60, 55, 25, 10, 70. I'll take 100. So totally 8 elements, one more element I'll take 65. Okay, we'll see the output. So we need to get the sorted order. You can see the sorting list is 10, 20, 25, 55, 60, 65, 70 and 100. So like this we can get the sorted order of heap sort. So how we can maintain? So everything we have seen. And coming to the next one in this, what is the complexity of heap sort? So the complexity of heap sort, so how it can be, anyway we can see in the program also. And first one, what we are doing, anyway I'll show you with that first. Anyway, first we have taken the elements. In order to make it into the heap, each element has to be ordered. Anyway, it takes not beyond n number of elements are there. We just have to arrange in the heap. In the worst case you will get n is a complexity. And then in order to make heap sort, okay, in order to make heap sort, when you want to retrieve in any binary tree, if you want to retrieve an element, so mostly it is log n, right? Log n is a complexity to take an element, and here you have to rearrange the elements. So in a worst case it will take n, right, for rearranging. So n plus n log n mostly it is. So that's why it is not going beyond n log n. So that is advantage if you take the concept of binary trees. Again here you will get the concept of you will get the complexity as n log n only, even in the, of course, in the best case, worst case and average case. So like this we'll get the concept like heap sort. So we have completed about heap sort now. So in the next we'll see, of course, till now the total 6 sorting techniques which are all based on comparisons. Next we'll see these things which are not based on comparisons. So what we call it as, okay, we'll see these 3 things, the sorting, and not only that, the strings also we'll see in the next video lectures. Thank you.